Hello everyone. In this lecture, we are going to learn how to generate random numbers using inverse transform method. We learned how to generate random numbers from these built-in functions in R. But what if you get a distribution outside this list? There are few other ways to generate random numbers. One such approach is inverse transform method. You can use inverse transform method to generate random numbers from any continuous distribution. The inverse transformation method is based on this theorem. This theorem is called probability integral transformation. Let's look at the theorem first. The theorem says let x be a continuous let x have a continuous CDF fx and define the random variable y where y equals capital Fxx, then y follows a uniform distribution with parameters 0, 1. So here what the theorem says is you have a random variable x and the CDF or the cumulative density function of this random variable, a cumulative distribution function of this random variable is Fxx. Based on this cumulative distribution function, we create a new random variable called y. We create a new random variable. So now instead of simple x, so we write capital X here. Because now it's a random variable. Instead of simple x, we substitute all simple x's in this formula using capital X. The theorem says this new random variable capital Y follows a uniform distribution with parameters 0 and 1. So if you construct the CDF of Y, so that's Fyy, this is probability Y less than or equal simple Y. So we can compute this one, 0 to, let's couple this y. The distribution function is 1 dt. Because we know for example, suppose if you have a random variable called q. Suppose q follows a uniform distribution with parameters a and b. Then the continuous distribution function of q is 1 divided by b minus a. Here we, instead of a and b, we have 0. This one 0. So in this case, the fy, the distribution probability density function of fy is 1. So that's why I have 1 here. If I simplify this one, you will get the y. This is what we have here. Probability y, probability capital Y less than or equal simple y equals simple y. This is actually the definition of the uniform distribution. This is actually the CDF of the uniform distribution with parameters 0 and 1. Okay, let's try to understand this using an example. Suppose x has an exponential distribution with lambda equals 1, then we can write the probability density function like this. In general, the distribution of exponential with parameter lambda is fxx, lambda e to the power minus lambda x greater than 0, and lambda greater than 0. Now here we substitute lambda equals 1. Let's derive the CDF fxx. This is We need to integrate from 0 to x e to the power minus t dt. So you will get 1 minus e to the power minus x, where x greater than 0. So based on this, we can define a new random variable, capital X. Now I have to substitute capital X instead of simple x. According to the theorem, if x follows an exponential distribution with parameter 1, then the new random variable y minus e to the power minus x follows a uniform distribution with 0, 1. This is the random variable formed by its CDF. And this new random variable will always have a uniform distribution with parameters 0 and 1. Before proving the theorem, let's look at some important results of fx inverse, the inverse of the CDF. The first result is if fx is strictly increasing, then inverse is well defined by this. This is the visual demonstration. Here we have x. This is the CDF. Here we are referring to a strictly increasing function. So it looks like this. Maximum is 1 because this is a CDF. Minimum is 0. And if this is x, we have here fxx. Let's call this new quantity y. Now, if we start from here, and move the other way, we come to the same point. Now we can call this fx inverse y. So this is equal to x. So in this equation, this side is represented by the equation here, and this side is represented by the equation here. However, if x is constant on some interval, then fx inverse is not well defined by this. To avoid this problem, we define fx inverse y using this. Again, this is the visual demonstration. We have x here. This is the CDF. This is increasing and then constant and again increasing. Maximum is 1. This is 0. Let's call this one x1 and x2. Again, this value is fx simple x. Now in this case, any x satisfying x1 greater than or equals x less than or equals x2 satisfies fxx equal y. So now if we move the other way around, there's one x1 here, and again we have several x values. Any value within this range. Earlier we just have one single point. So this problem is avoided by defining fx inverse y using this. Now we are referring to the infimum within this range. In this case, the infimum is x1. So according to the definition here, in this case, fx inverse y equals x1. This definition is valid for this one as well as this one. This definition is suitable to in a case where you get a strictly increasing function. But this definition is not valid for a case like this. This function is strictly increasing. This function here is non-decreasing. It is not strictly increasing because it is constant within this range. Okay, now let's look at the second result. If fx is strictly increasing, then it is true that fx inverse fx simple x equals simple x. This is the visual demonstration. We have here x, here fx simple x. We are referring to a strictly increasing function like this. Maximum is 1, minimum is 0. Now, so this is fx x. Let's consider a point here, simple x. Now if you move towards this direction, you will get fx simple x. What about the other way around? If we consider the fx inverse of this, then that means you start from here and move towards the other way around. We come to the same position, and we can write it as fx inverse fxx. So now we can see simple x is equal to fx inverse fxx. The green one is fx inverse. However, if fx is flat, it may be that I will tag the space here. If fx is flat, it may be that fx inverse fxx not equals simple x. So this is the visual demonstration. You have x and here CDF. Up to this point increasing, then constant, again increasing. Maximum is 1 and here 0. This point is x1, this point is x2. Now, according to the previous definition, fx inverse fxx, so this one is fxx, is x1 for any x within this range, including x1 and x2. Even with this case, it is true that probability capital X less than or equals simple x. This is equal to probability X less than or equal x1 for any x within x1, x2, including x1 and x2. Now we can, okay, now let's prove the theorem. The theorem says if x takes the CDF fxx, then the random variable created from its CDF follows a uniform distribution with parameters 0 and 1. So what you need to show is you need to show that the CDF of y takes the form of the CDF of the standard uniform distribution. Or else what you need to show is you need to show the probability less than or equals y takes the form of the standard uniform distribution. And another example is if you're asked to show that the variable z follows an exponential distribution with parameter lambda, what you need to show is you need to show the CDF of z takes the form of the CDF of the exponential distribution lambda. So in this case, we need to show that the y or the CDF of y takes the form of the standard uniform distribution. Okay. So if we consider let's say you have a random variable called u and the uniform and this follows a uniform distribution with parameters 0, 1, we know that the CDF is equals to u, where u is between 0 and 1. So we can derive this one. We derived this one before as well. So this is, you have to integrate this one, 1t, then you will get t. This is FUU. Okay. So in other words, here we have to show this is equal to y. This is what we need to show. Okay. Let's start from this side. Probability y less than or equals simple y. I can substitute for y probability fxx less than or equals simple y using this. Now let's take the inverse from both sides. Fxx, and I take the inverse of this one. Still, this less than or equal is valid because fx inverse is increasing. Now, according to our results, we can write this one as x less than or equal fx inverse y. Now you can see this is the definition of the CDF of x. This equals y. So that means the random variable y follows a uniform distribution with parameters 0, 1. If this step is not clear, it's like this. The definition of the random variable CDF. Let's say fxx. According to the definition, this is capital X less than or equal simple x. So this x here, it corresponds to here. Similarly here, this x is here. And this term here corresponds to this one. So here in this case, this term here goes here. So now we have proved that the CDF takes the form of the CDF of the standard uniform distribution, like this. We have proved probability y less than or equals y is equal to y. In other words, we showed that the CDF of y takes the form of the CDF of the standard uniform distribution. Now let's see how to use this theorem to generate a set of random numbers from a particular distribution. So according to the theorem, if x follows a probability density function fxx, then the random variable formed by its CDF, that is fx capital X, follows a uniform distribution with parameters 0, 1. Now here we are thinking about the other way around. Can we transform a set of uniform random numbers by the inverse of the CDF and get the random numbers of x? Yes, we can. We can use inverse transform method to generate random numbers from x. The inverse transform method can be used to generate random numbers from any continuous distribution. Let's try to understand this using an example. Suppose x follows an exponential distribution. Okay. Suppose x follows an exponential distribution with value 1. Now we want to generate random numbers from x using the inverse transform method. I can show that the CDF of x is equal to 1 minus e to the power minus x, where x greater than 0. Now according to the theorem, we have 1 minus e to the power minus capital F. This is equal to u. This follows a uniform distribution with parameters 0 and 1. We have u 1 minus e to the power minus 6. Now we solve this equation for x, then you will get x minus log 1 minus u. And we can write this one as fx inverse u minus log 1 minus u. Then our theorem implies if u follows a uniform distribution with parameters 0 and 1, then minus log 1 minus u follows exponential distribution with parameter 1. This is exactly the other way, the opposite. When we move from here to here, we consider the CDF. Now we are considering the inverse of the CDF. The random variable formed by the inverse of the CDF. That's minus log 1 minus u. So if it is required to generate a random sample from x, then we need to generate random numbers from uniform 0, 1 distribution and substitute to the equation here. So in other words, if we generate u1, u2 up to un from uniform 0, 1, then yi values, that's minus log 1 minus ui, we substitute these values here where I goes from 1 to n. Now these new random values, these new values are independently and identically distributed, and these new random variables are generated from this distribution here, or the exponential distribution with parameters lambda. So if in order to get the set of random numbers from x, what you need to do is you need to generate a set of random numbers from uniform distribution and substitute to the formula here. Then we get a set of random numbers from the distribution of x, or in this case exponential 1. Okay, let's go to an example. So these are the steps in deriving random numbers using integral transform method. First, you have to derive the CDF of fx. Then you have to derive the inverse of the CDF. After that, you can write a function. Inside the function, it should generate a set of random numbers from the uniform distribution. And then you substitute to the formula here to get the random numbers from x. So here the first example, write a function to generate n random numbers from the distribution with density fxx 3x squared, where x is between 0 and 1. So the step 1, we need to derive the CDF. This one. So we have fx 0 to integrate from 0 to x. So here we have x cubed, and this is x is in between 0 and 1. The second step is you need to compute fx inverse u. So for that you have to substitute u equals x cubed, and here you have to solve this equation for x. Now you can write f inverse x u is equal to this. So after that, you have to write an R code or R function to generate a set of random numbers from the distribution of x. In our case, fxx, this is 3x squared, where x is between 0 and 1. Now we are writing a function to generate random numbers from this distribution. Okay, so the name of the function is generate IT, inverse transform. And here my input is n, number of data points that you want to generate from this, number of random numbers you want to generate from the distribution of x. Then open bracket, curly brackets and close brackets. Here this one is the function body. We first generate a set of random numbers from the standard uniform distribution. We generate n random numbers from the standard uniform distribution. That's uniform 0, 1. After that, in order to get the random numbers of x, then you have to substitute u values to this formula. So this u to the power 1 divided by 3. Now after that, you have to return the values of corresponds to the xgen. So when you type set.c 2020, this is to make your results reproducible, and generate it, then you will get 10 random numbers from this distribution. Here you have 10 random numbers from fxx. Let's try to visualize these distributions. First, the theoretical distribution. The theoretical distribution is fxx, this one. So we were given that the range of x is between 0 and 1. So I generate first x value 0, 1 and increment is 0.01. Then I generate corresponding fx values. So here we have x values, here we have fxx values. So this is equal to 3 multiplied by x to the power squared. Since we use a table format, we can create new random variables based on the existing variables. Now you can use the ggplot to draw the theoretical distribution. So the name of the data frame, x value is this x and this y values, and my geometric object is geom_line, and I can color the line by I can give a color to the line. So this is the empirical distribution, the distribution generated based on the data. So the empirical distribution, the distribution that's drawn based on the data that we generated from X. So for that, I generated 1000 random numbers from this distribution and store it inside a variable, inside a data frame called empirical.df. Then I draw a histogram for the data that we generated. Empirical df x is data.emp, and my histogram, and I use geom histogram. In this case, I don't need to specify y. The default y variable is something like this, count. Now you can see you are getting counts here. So I use empirical df, x is the values that we have generated based on the function that we have written before, and the color is white, that's the width, and the bin width is 0.05. So default, you are getting counts in the y-axis. If you want to change this one to density, you have to pass this one. 2 dots, density, again 2 dots. If you do not pass anything, the default y value is dots, counts, dots. If you want to get the density instead of the counts, you have to pass it like this. Now, if you want, this is important if you want to draw both the theoretical distribution and the empirical distributions together. By drawing theoretical distribution and empirical distribution together, you can check if your results are correct. When you increase the number of data random numbers, here we used 1000, you will see that the empirical distribution is getting closer to the theoretical distribution. In order to draw the both empirical and theoretical distribution, now here I start with empirical df, x is data emp and y is density. And this part is this part is corresponding to this one. Now I want to add another layer on top of this graph, another geometric layer. So I use geom_line, and the data corresponds to this new line is inside the theoretical df. So I have to define inside this geometric layer, we have to define another data set, theoretical df x and the corresponding fx value. Then you can see the empirical distribution as well as the theoretical distribution. Here I modify the function. When you run this function, you will get the random numbers as well as the distribution. So first generate random numbers from the uniform distribution, and then substitute values to the inverse function, and then output xgen. After that, I store those I store those values inside empirical.tf. Here I generate values for my theoretical distribution. Since now I have multiple outputs, I store the output inside a list function. These outputs are not homogeneous, they are heterogeneous. One output is a set of random numbers, the other output is the plot. So the first one is xgen, and I use comma to separate the second one. So the second output is my ggplot, comma. This gives random numbers. This gives the empirical distribution together with the theoretical distribution. So when you run this command in 100, it will generate 100 random numbers from X, and it will plot the theoretical distribution and empirical distribution together. You will get both if you run in 100. If you just wanted to extract only the set of random numbers, you have to extract the first element in the list. If you want to extract only the plot, that means you have to extract the second element in the list. So in this case, you will get the plot. Here you will get the random numbers. Here you are getting the plot. If you use just the command in 100, you will get both the random numbers and the plot. And here the output type is list. Here this one is the first element of the list. This one is the second element of the list. Let's look at the second example. Write a function to generate random numbers from the exponential distribution with parameter lambda using the inverse transform method. So first, we need to show that we are given x follows an exponential distribution with lambda, and we need to show that fx, we need to derive the CDF of x. You can show that this is equal to 1 minus e to the power minus lambda x, where x greater than 0. This is the first step. Next, you have to derive the inverse of x. So this is u 1 minus e to the power minus lambda x. You have to solve this equation for x. When you solve this equation for x, you will get x minus 1 divided by lambda log 1 minus u. So now this is fx inverse u minus 1 divided by lambda log 1 minus u. So now you can write a function to generate random numbers from the exponential distribution lambda. Actually, we have a built-in function to generate random numbers from the exponential distribution with parameter lambda. But what we're trying here is we try to use inverse transform method to generate random numbers from the exponential distribution. So here my name of the function is exp generator, and I have two inputs in the number of random numbers that you want to generate, and lambda is the value. User can pass a value for lambda. First, generate random numbers from the uniform distribution, and then substitute to the formula here. So now we are getting random numbers from exponential distribution with parameter lambda. So here I generated 1000 random numbers from the exponential distribution with lambda. To make the results reproducible, I set the seed to 111. And now we get EXP generator. This is 1000, this is 2. You will get 1000 random numbers like this. Next, graph the density of the sample with the exponential 2 density superimposed for comparison. This is similar to what we did before. First, I stored the data under empirical df.exp. Then here I wrote a code to plot the theoretical df. And then I use ggplot to draw the empirical distribution and the theoretical distribution. So this is the this is the CD theoretical distribution, and the histogram denotes the empirical distribution. So now you can attempt the questions in the